Good morning, thank you all for being here. This talk is an introduction to the Semantic Web, which basically means that in the next 45 minutes I will explain to you what the Semantic Web is, which technologies power it, and we will show what these technologies are capable of, but also the limitations and the quirks we need to keep in mind when working with these technologies. That's quite a lot of ground to cover in 45 minutes, so we'll just provide an overview, leave out some of the details, but at the end I will provide you with some resources to read up on the rest if you're interested. So, well, what is a semantic web? Well, let's first talk about what semantic web is not. If you were hoping to get some good discussion here about the use of HTML tags, when you should use bold and when you should use strong, or a div instead of an article, you can probably still sneak out the back door there. This is not what the semantic web is about. It is about semantic meaning of things, which is related, but the semantic web is something different. Then what is it? Well, we can probably best illustrate by an example. And it is about finding information on the web. Suppose you're a huge fan of Ed Sheeran and you want to visit one of his next concerts. Well, then what would you do? You just open your web browser, go to his website, check the tour dates, and then you see that tomorrow there's a concert in St. Paul, Minneapolis. So you book your tickets and you prepare to go there, and you need to know what clothes to pack. So you want to check the weather for St. Paul, Minneapolis. So you open up your favorite weather website and you search for the weather for St. Paul, Minneapolis for tomorrow. And then you see that it will be 76 degrees. You think, whoo, that's hot. Don't know if I have clothes for that. But then you remember that the Americans use some crazy system for temperatures and that you need to convert temperature from degrees Fahrenheit to degrees Celsius. So you look up some Fahrenheit to Celsius formula and you do this calculation all by yourself, and then you know what the weather will be like. And this is what we kind of call Web 1.0. It's the web of documents, and it's meant for human consumption. So you have to find all your own information, interpret it yourself, and link it together all by yourself. And there's no software that could do that for you. And then came along Web 2.0, and we got APIs and feeds, and everything got so much better, so we could write software for it. But, well, with Web 2.0, Ed Sheeran could publish a feed of events on his website, but we still don't know everything. Is that feed iCalendar, or is it vCalendar? Maybe there are different types of events. We're only interested in a concert. There might also be charity events or something. And, well, our weather website maybe has an API, but how does that work? Do we need to provide XML or JSON? And which fields or properties are in the inputs and outputs? And which units are there? The example I showed you of the weather website didn't even note the units for the temperatures. And this is Web 2.0. It's a web of individual APIs. It's for consumption by specialized software. So if we want to use such an API, we have to write software that is specific to that API. And if we want to combine multiple APIs, we would have to write that software ourselves. And it's not really useful if every time we want to know this information, we need to write some piece of software for it. And this is what the semantic web aims to solve. In the semantic web, we would ask a question like, hey, what's the weather like at the place where Ed Sheeran will give his next concert, to some agent on our phone, for example Siri. And that agent would pull all kinds of information from the web, combines it and convert it to the format and the units we want, and then answer your question for you. And this is what we call the semantic web. Also, some people call it Web 3.0. And it's a web of linked data. All data on the web is linked together, and intelligent agents, or PAs, general purpose, can use that information to answer questions for you. So we don't have to write new software again and again. So this must be all shiny and new stuff, right? The web of the future. Well, the term semantic web was already coined by Tim Berners-Lee in 2001. And the semantic web is based on a couple of World Wide Web Consortium standards. And these standards are all kind of between 10 and 20 years old. So it's actually nothing new. It's only something that has finally gained some traction in the last years, mainly in research. But it's kind of starting a second life right now. So we'll look at some of these technologies and see what they can do for us. Let's first start with RDF, the Resource Description Framework, which is kind of the fundamental piece of the semantic web. And what does RDF do? Well, RDF records statements about things, kind of like XML file or a JSON file or a database. So, well, what can we do with RDF that we cannot do with these technologies already? Well, RDF has a special power, and that is that it allows you to read and merge and relay statements easily without knowing the actual contents of these statements, without understanding what they mean, and even infer new data from old data without exactly knowing what this data means. So how does that work? Well, let's first look at what an RDF file looks like. This is kind of an RDF file. It's just a giant table with 3 columns, and every row in this table represents a statement. So every statement has a subject, a predicate, and an object. And these are meant in a grammatical sense. So the subject is the thing we're saying something about, the predicate is the thing that we say about it, and the object is kind of a parameter to the predicate or the thing acted upon by the subject and predicates. And each statement just consists of these 3 parts, and that's why we also call such statements triples. So how does such an RDF statement look like? Well, we could start by entering some data about me. We could say that I work at Moxio, which is an awesome company, by the way. And then I would be the subject, works at would be the predicate, and Moxio, the object. And we could add some more data in the same fashion, like my Twitter handle, that I live in the city of Delft, which is in the Netherlands, and that Moxio is also based in Delft. And you could see the quotes around the Twitter handle, and that's because RDF distinguishes between things that only have data and things that have a kind of an identity. It's sort of the same as the distinction between entities and value objects. It doesn't really matter, but for now remember that for technical reasons we just put quotes around the data values to distinguish them from the things that have an identity. And we can see that some of the terms here, some of the subjects and objects occur multiple times in a list. So there are some statements that are related to each other. And we can make that explicit by providing some other representation of the same RDF data, which is as a graph. Here we have a graph of the same RDF data in which all the subjects and objects have become nodes and the predicates have become edges between them. And this is already starting to look like linked data. All these nodes are linked together by the predicates. Then, well, what's so special about this structure? Well, I talked about merging data from different sources and linking it together. Let's suppose next to the data you already saw, we have some other data set with information about the Netherlands. Let's say that it comes from a Lonely Planet guide or something. Data about the capital of the Netherlands and how much people live here. Suppose we want to combine these sources. Well, it's actually pretty easy. We have 2 tables, each with 3 columns, so we can just stick them together. Easy as that. And if we then convert this to a graph, we see that these data is now also connected. So we have linked these 2 data sets together just based on the common subjects and objects and predicates that are in them, just based on their names. For linking these data together, we didn't have to know what Delft is or what the Netherlands is. It just looked at the names and joined identical terms together. So this is kind of what RDF is, but how do I put this data in a file? Do I need to make a table in Microsoft Word and put all the names in it? Well, there are multiple ways to put RDF data into a file, different serialization formats. The most human readable form is called Turtle, and if you look especially at the things at the bottom, it kind of looks like the triples I showed you earlier in the table. There's also, for consumption by computers, there's RDF over XML, which is quite unreadable but parsable very well for computers. And there's JSON-LD or JSON-linked data, which is a kind of a way to embed semantic data into a JSON API. There's even RDFA, which allows you to embed RDF metadata into HTML markup. And I will not go into details about all these serialization formats because they don't matter. The thing that we have to remember is that RDF is an abstract data model. There are different serialization formats, but they're all just another way to write down this list of triples or this graph that we saw earlier, and the rest doesn't really matter. Let's talk about identity, because we saw that some things are joined together based on the name, but, well, there are things that have the same name. Like this, what you see here is the Amsterdam. It's not the city of Amsterdam, but it's a ship called Amsterdam. It was an 18th century ship that used to sell spices and other goods to the East Indies. And this is not actually the ship, because it's a replica. The original lies wrecked on the bottom of the English Channel, and this replica can be seen at the Scheepvaartmuseum, our National Maritime Museum, here in Amsterdam. And suppose that National Maritime Museum is very advanced and publishes some of its data about its ships as RDF. So we could have some data about the ship, like that it has 42 guns and that its current status is wrecked. And, well, suppose our agent finds this data, and it also finds the data from the Lonely Planet we saw earlier about the Netherlands, and we combine those two and we show that as a graph. Then we would get that the city that is the capital of the Netherlands has 42 guns and is currently wrecked. That's not really what we want. So we need some way to distinguish between the one thing named Amsterdam and the other thing named Amsterdam. So we need some way to identify these. Well, what do we use on the web for identification? Uniform resource identifiers. So instead of representing things by names, we start representing them by URIs. So for the ship Amsterdam, we could use some URI, in this case a URL that points to the website of the National Maritime Museum, some page there. And we do the same for the predicates. And for the city of Amsterdam, well, we could use some URL on the Lonely Planet website. And we have solved the problem. These URIs are different, so the concepts are different. These URIs get quite long, though. So this is not very practical when writing this data down ourselves. So we need a solution for that. Well, those familiar with XML namespacing may already have seen something like this. We use a qualified name. We split these URLs into a namespace part and a local name part, and then we define a mapping table with prefixes pointing to a certain namespace part, and then instead of the full URI, we use the prefix combined with the local name, which we also call a qualified name. And if we define such namespaces and namespace prefixes, we could just represent the concepts we saw earlier like this, with the prefix NMM for the National Maritime Museum and the prefix Lonely Planet for the Lonely Planet data. And note that we do not only prefix or represent by URI the subjects and objects like Amsterdam, but also the predicates like the status. So in this way we can distinguish between different uses of the verb status. Like in this case it represents the status of a ship, but well, the word status could also mean a marital status or something else. So by defining these based on a URI, we can make differences explicit. And for the examples in this talk, I will just use all kinds of namespace prefixes without defining them. You can probably figure out what they're supposed to mean. There are three fundamental laws that are associated with the semantic web, and these actually have to do with the messy and vast nature of the web with varying quality of data. And rather than try to work around this, the semantic web tries to embrace this messiness of the web. And this leads to these three fundamental laws that are commonly associated with the semantic web, but actually apply to the web as a whole. And the first of these laws has to do with the naming things we saw just. Suppose we have some data from Lonely Planet guides in different languages about the city of Brussels. They would probably all use a different namespace prefix for that city of Brussels. But they still represent the same thing. They still represent the same city. And also within one single namespace, we could have different names that still signify the same concept. Like within MI6, James Bond may also be known as 007. It's still the same person, it's the same secret agent. And this is called the non-unique naming assumption. Different names do not necessarily imply different concepts. The web has grown and people started using different things for different names for the same thing. So we may never assume that just because two people call something a different name, that it is actually a different concept. The second law has to do with truth and authority. Let's look at a tweet from our good old friend Donald Trump. And because Donald Trump is very modern, he also publishes his tweets as RDF. So he could say that Obama tapped him. And, well, a lot of people don't believe that this is true. And Donald Trump apparently believes it is. But it doesn't matter. On the web, he can just publish this and say it is, or, well, he can say that he thinks this is true. He doesn't need permission from anyone to do so. And it turns out that Donald Trump also has an opinion on PHP frameworks, which he also publishes as RDF. And for that, he uses some names in the PHP fig namespace. And as far as I know, Trump is not an authority on PHP frameworks, nor a member of the PHP fig, but he doesn't need to ask permission to use this PHP fig namespace. He can just say anything he wants. Like I can also say make statements about Donald Trump. So the use of namespaces are not limited to someone who has access to that namespace or something. We can just use any URI, any namespace that we want. And this is called the AAA slogan. On the web, anyone can say anything about any topic. So that applies to a bit of truth and authority. And it's also the power of the web. In the old days, you could just open Notepad, make an HTML page, put it online for the world to see. You didn't need permission from anyone to do so. And it's kind of the freedom of the web that can also work against us and that we have to keep in mind. The third law has to do with this slide. I could have stated here that my favorite color is blue, but I chose not to. What does that say about my favorite color? What do we know from this? Does that mean that my favorite color is not blue? We don't know. In the same fashion, since Donald Trump is apparently an expert on PHP frameworks, we could state that Donald Trump knows Symfony, Donald Trump knows Cake PHP, Donald Trump knows CodeIgniter. But what does this say about his knowledge of Laravel? We don't know. Just because it is not on this list, we cannot conclude that he doesn't know Laravel. And this is called the open world assumption. Since there's so much information on the web, and we never know if the information we have is complete, and we can thus never draw conclusions from absence of information. And these three laws are something to keep in mind when working with data on the web. So we know what RDF looks like, and we know what to keep in mind when working with data from the web. Now we want to query this. And for that, there's a language called SPARQL. And if our agent finds data on the web, RDF data, it probably first loads them into a triple store, which is just a fancy word for a database for RDF triples. It's kind of like a graph database, but just a bit more specialized. And then we can run some SPARQL queries against them. And SPARQL is actually like pattern matching on a graph database. So we just define kind of a graph of the data we want to have and put some placeholders in it. Here there's employee and company, and we just match these parts against the data, the graph of linked data that we have, and find which pairs match. So if we would run this against the example data we saw earlier, then we would get back that I work at Moxio, which is indeed a company based in Delft. And in the same fashion, we don't need to provide any fixed values in this. We can just put it full of placeholders, and anything that matches that pattern works. So we could ask about all employees living in a city where their company is also based, and then we would get back similar results. There are also online SPARQL endpoints against which we can run these queries. And the major one of them is DBpedia, which is actually all the data in the Wikipedia info boxes converted to RDF. Some people have put quite some effort into that. And we can also run some SPARQL queries against such an endpoint, just online. Like, well, of all the songs by the Beatles, give them to me in a list ordered by runtime descending. So if we would enter this into the SPARQL dbpds SPARQL endpoint, we would get back a list of Beatles songs ordered by runtime, and we could see that Dig It is apparently their longest song, with a runtime of about 15 minutes. You can also see here in the list that Dig It occurs multiple times. So apparently it has multiple versions, each with their own runtime, and they all occur in this list. These properties don't need to have one single value. So we have data, we know how to query it, but can we get some structure behind this data? Well, we know schema languages for XML and JSON, and RDF also has its own schema language, which is called RDF Schema. And RDF Schema, like JSON schema describes the structure of JSON in JSON, and XML schema describes the structure of XML in XML, RDF Schema describes the structure of RDF data in RDF. And RDF Schema has ways to denote classes, properties, the domain and range of properties, so the things that go to the left and right of those properties, what classes are they? And it has a kind of inheritance structure for classes and also inheritance of properties. And these RDF schema annotations can be put in the same file as the data or not. It doesn't matter because we can merge them easily anyway. So suppose, as an example, we have some data about Donald Trump again, this time that he is the father of Ivanka Trump. And we can add some RDF schema statements to that, like saying that is father of has a range of persons. So the thing to the left of the is father of is always a person. And its domain, so the thing, the range is the thing to the right, so that someone who is to the right of his father of is always a person, and that it has a domain of father, so the thing to the left of it must always be a father, because, well, then otherwise someone cannot be a father of someone. And we have kind of an inheritance structure, so father is a subclass of parent, because a father is always a parent, and a parent is a special form of a person. And we could also say that is father of is a subproperty of is parent of, so if X is father of Y, then also X is parent of Y. Now the main feature of RDFS is that from this data with its RDFS annotations, we can infer new triples. These are printed in italic. So from this data we can conclude that Ivanka Trump must be a person, because she's in the range of is father of, and the range of is father of is person. And we can also conclude that Donald Trump is a father, and therefore a parent, and therefore a person. And we can also conclude that Donald Trump is a parent of Ivanka Trump. You see here the use of RDF type, and that is kind of an instance of in RDF. So we just say that Ivanka Trump is an instance of person. And this process is called inference. So we have some triples, which we call the asserted triples, the triples that we state to be true. We put them through some software, which is called a reasoner, and we get back a list of inferred or virtual triples, the things that the reasoner added to the data based on the conclusions it draws. And this is a recursive process. We can feed back these inferred or virtual triples to the input of the reasoner and get back even more inferred or virtual triples. And typically, also, graph triple stores, when using SPARQL, these are also equipped with a reasoner. So it also reasons on the in-memory triples it has, and when we query the above data for something, well, just give me any person, even though we did not explicitly state that Donald Trump is a person, the reasoner knows from the data, and it draws its conclusions, and it knows, hey, Donald Trump is a person, and Ivanka Trump is also a person, so I must return them both, even though we did not explicitly state that. And these RDFS tools can easily be used to combine data from different sources. Suppose we have two data sources about the American presidential family. One that states that Donald Trump is a person, and the other data source states that Melania Trump is a human. Well, it's quite difficult to work with these two data sets if they use different names for something that's actually quite similar. We would also consider Melania Trump to be a person and Donald Trump to be a human. So we can write some RDFS to align these data sources to each other. So we use some mapping rules and we just say, well, let's just make person a subclass of human, so that every person is also a human. And otherwise, the other way around, we add that a human is a subclass of person, so that every human is also always a person. And if we then apply some reasoner on this, we would get back that Donald Trump is also a human and Melania Trump is also a person. And if we then put this into a triple store, get some SPARQL query on it, and we query for all humans or all persons, it doesn't matter anymore because they're considered equivalent and we would just get back them both. So this allows us to query different data sources as if they were one, by just mapping them together. There are some differences between RDF schema and JSON and XML schema. Suppose we have some data about MI6 agents, which says that James Bond is a secret agent and James Bond has a gun. Well, that's not that special, but you may have noticed we made a typo. We used the number of guns prefix pointing to the number of guns property from our National Maritime Museum. And our National Maritime Museum is also very modern, so they published an RDF schema for the data, which says that the domain of number of guns is a ship. So the thing that the number of guns applies to is a ship. And well, we would expect that if we put this through some RDFS capable reasoner, we would get back that we've made an error. Hey, you made a typo. You shouldn't have used the NMM number of guns, but maybe some other property, because the number of guns only applies to a ship. Well, it turns out that's not the case with RDFS. Our RDFS reasoner will just happily conclude that James Bond is a ship next to a secret agent. Things can have multiple types, and so this does not allow, this does not prevent something from having two types. And thus James Bond can be a secret agent and a ship at the same time. And this is just the way RDFS works. In fact, RDF schema will never consider data to be invalid, unlike JSON schema or XML schema. It may just draw some strange conclusions and will always assume that the data you entered is correct. There's another technology called the Web Ontology language, or OWL, because that sounded a lot better than WOL, probably. And that allows for even smarter inferencing. So we can see OWL as kind of as RDF++. And it gives even more and more powerful inferencing possibilities. There are elements of set theory, description language, goes quite in the direction of mathematics, which I really like. But this power comes at a price, and we will see that later. I will show some of the possibilities of OWL. There are inverse properties, so that if we say Donald Trump is a parent of Ivanka Trump, and we state that is parent of is the inverse of is child of, we could also reverse that statement, or well, rather our inferencer would do so. And it would conclude that Ivanka Trump then must be a child of Donald Trump by the inverse property relationship. There are also symmetric properties, so that we can state that Donald Trump is married to Melania Trump, and if is married to is a symmetric property, then we would know that it would also apply the other way around, so that Melania Trump must then also be married to Donald Trump. So this allows us to infer new data. There's also a concept of equality, so that if we say that Donald Trump is married to Melania Trump, and well, we solve that because of the non-unique naming assumption, there may be different names for the same concept. So we can say that Donald Trump is the same as the Don, as one of his nicknames would be. And then we can conclude that the Don is also married to Melania Trump, because, well, Donald Trump and the Don are considered the same subject by our reasoner. There are functional properties, which are properties which can only have one value. So if Ivanka Trump has father Donald Trump, and Ivanka Trump has as a father the Don, and we state that has father is a functional property, so it can only have one value, which makes sense if we're talking about a biological father, then our reasoner would conclude that the Don must be the same as Donald Trump, because Ivanka Trump can only have one father, so her two fathers must be the same person, actually. And the power of OWL can lead to some nasty situations, because now we can make data that is invalid. The first three statements are the same as before, and we just saw that from this data, our reasoner should conclude that Donald Trump and the Don are the same thing. But now we add some triple that explicitly states that the Don is different from Donald Trump. So our reasoner now should think that the Don and Donald Trump are different and that they are the same at the same time. And this is what's called an inconsistency. And our reasoner will tell us that it is. And our reasoner will in fact give up. The power of OWL lets us contradict ourselves and make constructs that are impossible to reason about. So our reasoner will give up and not draw any conclusion anymore for us. It will kind of try to point out where the error is. And these explanations are usually quite obscure, so it may take some time to find what went wrong. And that's also a major problem with OWL, because the reasoner cannot conclude anything anymore. When there's an inconsistency, it also gets quite difficult to see where exactly the error is made. And this is kind of how it is with OWL. It's okay to be inconsistent. You may remember the AAA slogan. On the web, we can say anything about any topic. So it's also okay to say things that contradict themselves. But a reasoner will never help you anymore. And that's kind of the deal with this. So, suppose you're all excited now about these semantic web technologies and you want to learn some more about them or read more on them. How to move on from here? Well, let's start with a small self-test to see whether you've been paying attention the last half an hour. We have some RDF data. Let's say George has a child Michelle and George has a child James. Now the question is, how many children does George have? Who thinks that George has 2 children? See some hands for 2. People for 2 or more? 2 or more. 1 or more? We don't know at all? Maybe? Okay. We can argue a bit about this, but it would probably either be 1 or more, or we don't know at all. There can be more than the ones we see here, because of the open world assumption. We never have all the information, so there may be other children we never know about. And there's a non-unique naming assumption. Michelle and James, although it seems unlikely, they may be the same people. They may be the same person. It may be that Michelle used to be James or something, or that Michelle is called James by her friends for some obscure reason. So it could be that James and Michelle are in fact the same child, so that George only has 1 child. And well, by the AAA slogan, anyone can say anything about any topic. We might even say, we don't know, this may be all completely untrue. It's possible. It kind of depends on how much we trust our data source, probably. Well, when using the semantic web, there's obviously some network effect. How more people use it, the more value you get from it. And using the semantic web is only useful if multiple parties speak the same language, because if they use the same concept, the same URIs, we can link this data together to form a giant graph of data. And only then does the concept of linked data really work. So it's impossible to align with existing vocabularies, data that's already out there. That doesn't mean that we can only use existing vocabularies. We could also use our own vocabulary, but provide some mapping rules to align them or to link them to the data already out there. We have seen how we can do so with RDFS subclass of, and there's subproperty of, which we can use to link data together. Same as or inverse of allow us to use our own vocabulary, but link it to the data already out there so that reasoners know that we're actually saying the same as other people are saying, or saying similar things. There are a lot of existing vocabularies already out there. One of the most famous, one of the ones with which it all started, is Dublin Core. And that's a vocabulary about metadata for publications and authors. And you may incidentally have already added some of these metadata to your website. You can embed it in HTML. There's Friend of a Friend, which was kind of a vocabulary for social networks before social networks became cool. Good Relations is a vocabulary for products and prices in e-commerce, and that is what allows different websites to compare prices from web shops, and what allows Google to compare prices from web shops. There's the CBNL, which is a Dutch vocabulary for construction and infrastructure and spatial planning. That's getting some traction. There's QUDT, which is a vocabulary by NASA, which allows you to explicitly state quantities and units and dimensions of physical things, and even allows these data to be converted by a reasoner. So the problem we had with the degrees Fahrenheit and the degrees Celsius would be solved automatically for us. If the data was in Fahrenheit, but we wanted Celsius, it would be converted automatically. In terms of software resources, the Semantic Web is kind of a Java world, so most software is written in Java. The go-to framework is Apache Jena. It's a whole Semantic Web framework and tools, but it is written in Java. There are 2 PHP libraries that are used in some places. There are open source OWL reasoners, Fact++, Hermit, and Palette. They're all quite good. And there's an IDE called Protégé, from which also the screenshot was with the inconsistencies, which allows you to edit RDF data easily, save it using multiple serialization formats, and it has plugins for reasoners, the 3 above it, that also allows you to apply a reasoner to your data. In terms of books, Semantic Web for the Working Ontologist is kind of the Bible on the Semantic Web, and I can highly recommend this book if you want to know more about this. There are also some resources on the web. The World Wide Web Consortium has quite some pages on the whole overview of the Semantic Web, the different technologies like RDF and OWL and SPARQL. There are also some good sources of online linked data. We saw DBpedia. There's data.gov from the American government, and there's also LOD Cloud, Linked Open Data Cloud, which provides you with an entry point to find different data sets about different subjects. This was my talk. Please leave your feedback on JoinIn. Tell me what was good about this talk, what can be improved. I really like to make this talk better. If you have any questions, you can ask them now or reach out to me somewhere here in the hallway or via Twitter. Thank you. I already saw some question there.
So there are many RDF
Yeah.
So are there also that actually link these together, so that you can search for something and it tells you which
vocabulary to use? Yeah. So the question is, there's lots of data out there. How do we find the data that we need? I think that's one of the open problems with the Semantic Web in its original vision. And I think that the World Wide Web Consortium will probably be working about technologies for finding this. For now, there are websites like the linked open data clouds that you saw, which kind of provide entry points or a catalog of data. But for this to be done in an automatic fashion, like Siri or something would, I don't think that that's a solved problem yet. And that's probably one of the reasons that adoption of the semantic web in its original vision is very slow.
Wouldn't that be as simple as set up a vocabulary that, say, links music to certain other vocabulary?
Maybe there could be a vocabulary that describes datasets as kind of metadata, but then still you would need to find all these datasets on the internet to know what's actually in them and what things they link together. So the problem, well, you probably need some crawler and a database that can store millions and millions of rows. Any more questions? All right, then thank you very much.